So, I'm not going to summarize what we did yesterday because that's all should be in the notes. So I'm just going to plow on ahead from where we left off. So, as you recall, we left off discussing pions and the idea of spurions, which is parameters that explicitly break symmetries, and how for the case of pions, the electromagnetic coupling of the charged pion to the photon explicitly broke any symmetries that could have kept it light, and so that gives us an idea about how corrections from the UV completion of the theory concerning pions, which is known as the Chiral-Lagrangian, how those corrections would feed in to corrections to the pion mass. And so that was fun, but we want to get back to the question at hand, which is, what sort of BSM could show up at high luminosity LHC. And so from the idea of discussing the pions was to give you a sense of how these things work as we go ahead and discuss now the Higgs boson. So the Higgs is, the theory of the Higgs at the electroweak scale is not totally dissimilar to the theory of pions. There are differences, but it's not totally dissimilar. And so if we want to work in an analogy with that, we can also perform a similar exercise and consider the parameters that there are in the electroweak theory, which explicitly break symmetries that could have kept the Higgs light. And there are two that are particularly interesting, which is the Yukawa interaction. Particularly the top is the most important bit, QUC. And there are also the gauge interactions. I'm just sketching them, so I've taken care in the notes to get my factors of I and 2 and things like this correct, but I will not do so on the board. And there's the gauge interactions, which look like this. And you see this is very much similar to what we had for pions. And so, following the same sort of logic, we would expect that whatever the UV completion of the standard model is, we know it exists, it should exist, but whatever it is, we expect it to give corrections to the Higgs mass, which are at least of order something like something in a way that is proportional to the top Yukawa squared, and or the gauge coupling squared. Where the lambdas here are just sort of a short notation for the typical mass scales that we would expect in whatever that UV theory is. So this is completely analogous to the pion. Now this isn't something that is at the level of a mathematical theorem, but it's just something that tends to always, there's no example where it hasn't arisen whenever you have a UV completion with some mass scale. If you have no symmetry protecting the IR fields, then they tend to get mass corrections. But these numbers are not strict. There could be an order 1 factor in front of here and an order 1 factor in front of here. If you can find a way of UV completing a theory like this involving a scalar, where there is no extra symmetry that protects the scalar, and these sorts of corrections don't show up, then please let me know, and we will start collaborating immediately, and I'll work day and night to make to bring your theory to the masses. Okay, so this is already telling us that if we follow similar logic as works for the pions, we would have expected the mass scale associated to new physics, if we weren't going to have corrections to the Higgs mass that aren't too big, to be less than or equal to, let's say here, around something like 400 or 500 GeV. Okay, this is the sort of logic that one had for decades, but particularly pronounced in the lead up to the switch on of the LHC. And this is essentially the logic, one way or another, that many people were excited that something was going to show up at the LHC very soon. In particular, if you look at this correction, it involves the top sector, and so one would have expected that if it's involving the top sector, that colored particles could show up, whatever the UV completion is, because if the UV scale was even further away, then the only way to make that consistent with having a small Higgs mass would have been to somehow fine-tune these corrections, these types of corrections against one another, which is of course a possibility. But when one is fine-tuning parameters, then you're essentially saying, as theorists, we don't, theories aren't recipes, right? We're not cooking in our kitchen. We're trying to guess at how nature works. And so people theorists generally tend to be less inclined to think that theories that are fine-tuned are plausibly could be describing how nature works, because there's no rationale for why nature would want to fine-tune those parameters. And that's a discussion we can have. If anyone has questions, we can take some time out to discuss it. But it's essentially saying that if this were to be real, if the UV completion were to be further away than say 500 GeV, one would have to fine-tune the Higgs mass. And so that fine-tuning essentially puts a sort of a bias against on your priors for whether or not you think that theory that you're working with, that UV completion that you're working with, might actually be correct or not. Nonetheless, the LHC was switched on by arguments like this. A lot of people thought that there were going to be spectacular signatures of new colored particles showing up. Because you're colliding protons, you've got a lot of gluons and quarks around, so you should have easy access to colored particles. And they didn't show up. And so this leads us to ask, essentially, what on earth is going on? People have said it using much more colorful language than that. And there was a lot of confusion. And so what I aim to do in this lecture, which might, depending on how tired you are, be split in two, but this 2-hour block, I want to discuss a little bit in more detail about the sort of things, when you have theories that can address these sorts of questions, what sort of signatures might show up at the high luminosity LHC, and what the current status of these questions like fine-tuning and so on are. And also I want to bring to your attention some sort of slightly more exotic theories that are sort of maybe in the minority of theories that people consider, but they're very interesting. One class, which I'll come to, is known as the twin Higgs. It's very interesting and has some very peculiar collider signatures that I think are very exciting and also very promising for something like high luminosity LHC for reasons that you'll understand from yesterday's lecture. Okay, so are there any questions about this before we plow on ahead? Yep. Yeah, exactly. So actually, it's definitely more than 500 GeV. If it's colored, because we'll see the limits are already at the TeV level. But the logic was that you can't forbid these sorts of corrections. The numbers in front might differ, but you can't forbid them. So if it were more than 500 GeV, you would get a too large Higgs mass, and so you need to have something cancelling that contribution. If it were lighter, say it was one would have imagined that it could be, say, 300 or 400 GeV, then there wouldn't be a problem, because if this contribution is too small, that's okay, because you can have other contributions to the Higgs mass. But we would have seen it. And so actually, this is already telling us, we'll come back to it, that essentially the limits are more like a TeV at the moment. So we already naively expect that theories like this would be fine-tuned at like the 10% level. Does that answer your question? Okay, excellent. Okay, so let's carry on. So I'm going to stick with the analogy and go into a little bit more detail, because it'll be useful for what I'm going to discuss and for the twin Higgs in a little bit. I'm going to discuss a little bit more detail this idea that the Higgs could be sort of like a pion. And the sort of, I say a pion because I want to be as broad as possible. A pion is known as a pseudo-Goldstone boson. I'll unpack that jargon for you in a few minutes. But what I'm going to say applies to things that you may have heard of, like composite Higgs models. But I want to try and couch it in a language that's a little bit broader than that. So I'm going to call it pion-like, which is a little bit broader if there are theories that don't necessarily involve the Higgs being composite per se, where it could emerge as something that has properties like a pion. So the idea is basically built on a building block which is many decades old, which is known as Goldstone's theorem. Nambu also played an important role in this. Who is familiar with Goldstone's theorem? Who's heard of Goldstone's theorem? Okay, basically everyone. Who feels like they understand Goldstone's theorem? No, is everyone? Okay, no. So okay, there's a discrepancy there. So basically, Goldstone's theorem states the following. So if you have some global symmetry, so this is not a gauge symmetry. This is something like, like a U1 rotation, where you're just multiplying the fields by a complex phase, like we discussed for lepton number yesterday. If you have a global symmetry which is spontaneously broken, then you will get, and if it were really a true global symmetry, so nothing was explicitly breaking that symmetry, then you will get a bunch of massless scalar fields, and the number of massless scalar fields that you will get corresponds to the number of symmetries that were broken, essentially. Massless is actually a bit of an understatement. I think what's more important to keep in mind is that these scalar fields, they won't just be massless, they won't have any scalar potential at all. So you'll have seen this picture where you have like a Mexican hat potential, and you sit at the top and then the field rolls down to the side of the Mexican hat potential. And the important thing is that as you're going around the bottom of that Mexican hat, if it's exactly horizontal, then it doesn't cost you any energy. You don't have to go up to go around. And that's why those fields, it's not that they just don't have mass, they have no potential, because there's zero energy cost to moving them around the bottom of the potential. So if you give them a kick, you can make it move, like create a fluctuation, by giving a kick of essentially infinitesimally small energy. So it costs you nothing to excite these modes. So those are the Goldstone bosons. So this is a way of guaranteeing that a scalar field is exactly massless and completely, and this symmetry protects it. So there's nothing that you could ever do to create a mass or potential for this scalar field unless you started to break the symmetry. Okay, and that's what happens for pions. That's why pions are light. Essentially, if you didn't have the QED, if you switched a few things off, like the quark masses and the gauge interactions, the pions could have been exactly massless. Okay, I'm just going to sketch what this looks like in a toy example. So, just to make you a little bit more familiar, but it's the usual Mexican hat type example. So imagine we have a single scalar field. It has the usual kinetic terms. And some potential, you could be much more general, but I'm just going to write the usual Mexican hat one. So you can see the shape of this. There's a quartic interaction, a negative mass squared, and just some constant, which is unphysical. So it looks like the usual Mexican hat if you plot it in terms of the magnitude of this field. One can parameterize, so this is a complex scalar field, one can parameterize it any way you want. But as always, there are smart ways of doing it, and there are not so smart ways of doing it. One smart way of doing it is to parameterize in what's known as the nonlinear representation. So I'm going to assume that this field is some constant plus one of the degrees of freedom. It's like the radial mode, when you write your complex numbers with in polar coordinates. You're doing this. E to the I theta over f. Okay, so theta is a space-time field, a scalar field, and rho is a scalar field, and so they are both, this is enough to parameterize all the degrees of freedom of this complex scalar field. You could have written it as like real part plus I imaginary part, that's perfectly fine, but this notation is just going to make life a little bit simpler. So we can plug this in, and when you plug it in, you get a theory that looks like this. You get, oh sorry, let's call that sigma. Sigma, thanks. D mu sigma plus 1/2 1 plus sigma over f. Sorry, my writing's not great. D mu theta. And you have a scalar potential, which looks like this, lambda over 8, 2f sigma plus sigma squared to squared. So this is just the usual Higgs potential. But you see that theta makes no appearance here, because it's essentially because of this, phi squared. So the e to the I theta and e to the minus I theta cancel. So this is what it looks like. So something you expect in any theory where you have Goldstone bosons is not guaranteed, but what you expect is that you have the massless Goldstone boson and some field that we usually call the radial mode, which is heavy. You look at the mass of this thing here, the mass is what lambda, the mass squared is lambda f squared when you square this thing out. And it has a cubic interaction and a quartic interaction. It's just the same as the Higgs sector of the Standard Model. Okay, so that's essentially a crash course in Goldstone bosons, or Nambu-Goldstone bosons more fairly. But then we can also see how you can generate a potential for these Goldstone bosons if you start to introduce interactions which explicitly break the symmetry. So once you've broken, it was this symmetry, this exact U1 symmetry, right? I can multiply phi by e to the I alpha or something, some phase, and the whole theory remains the same. So that's the symmetry. Down here you can't see it so clearly, but actually what that symmetry corresponds to is that, you know, up here I could go e phi goes to e to the I, I'll call it alpha phi. Alpha is not a field, it's just some number. This theory remains the same. The symmetry is pretty clear here. It turns out that the symmetry remains down here, but what the symmetry corresponds to is that theta goes to theta plus alpha f. So the symmetry never went away. This is why it's sort of an unpleasant historical accident that we call it spontaneous symmetry breaking, because the symmetry is never broken. It's there the whole time. It's just it just looks different in the two different phases of the theory. And you can see that because this symmetry corresponds to going around the bottom of that Mexican hat potential, and you can see that the Mexican hat is rotationally invariant. So that symmetry is still there, even though it has the lump in the middle. Okay.
Sorry, I think that the way you define theta doesn't have 1 over f in the exponential. You want to have dimension 1. It's not an angle. I think it's a theta.
So theta here?
Yeah, I understand. Just notation, like
yes.
Like d mu theta. So theta is dimension 1.
Yep.
So then there, theta over f.
It's dimensionless.
Sorry, yes, we are normalizing that.
Okay, so explicit symmetry breaking. So the symmetry, the same symmetry which you see down here as being a shift symmetry, is keeping this this field from getting any potential or mass or anything like that. But that means that if you start to break the symmetry, if you introduce interactions that break it, then you will generate a potential for the field. And so one simple example you could do, imagine we added to this theory a term, let's call it delta L. Sorry for this scratchy chalk. If we added a term that looked like lambda tilde phi to the 4 plus phi star, the conjugate to the 4, this term here. If we plug in this notation, this will generate something for you that looks like lambda tilde over 4 f plus sigma squared, to the 4, multiplying cosine of 4 theta over f. So sigma is a field here, but this is f. So what you've generated here is a potential for theta. So now it's no longer a Goldstone boson, it's a pseudo-Goldstone boson, because there's some explicit breaking, which is this lambda tilde. So there are a few things to note about this. One is that this lambda tilde is the only parameter in the theory that breaks the symmetry. And so in the UV or the IR, whatever's going on in your theory, if this is the only parameter in the theory that breaks the symmetry, then you don't get additional extra contributions that break the symmetry. They will always be proportional to lambda. To lambda tilde. So if lambda tilde started off small, it will stay small. There's no reason for it to suddenly become big, which means then that it can be naturally, we say, as small as you like. It could be a tiny number and the theory is stable. And what that means is that this field theta can have a potential which is naturally as small as you like. There's nothing that's going to suddenly make it bigger all of a sudden. And the mass is just the second derivative of the potential. So this field theta can have a mass which is naturally small. And this is exactly why the pions are so much lighter than the rho meson. This is the reason, because essentially the quark masses are the biggest parameter in the theory, which explicitly breaks the global symmetry that the pions emerged from. And that quark mass, the light quark masses are pretty small parameters compared to the QCD scale. The QCD scale you should think of as being the F, thereabouts, well, not quite, but thereabouts. And the quark masses are around, 4 or 5 MeV. So that's why the pions are light. So now we want to talk about the Higgs. So could the Higgs be a PNGB? By the way, if there are any questions about any of that, just shout out. If we spend a bit more time on one thing, I can just spend a bit less time on something later or just cut it entirely. We're totally flexible. The most important thing is that you understand a bit. Yep.
Isn't the standard expansion of the Higgs potential that I've seen?
Yes.
I am just a little bit confused. I suppose maybe it isn't an issue, but the fact that, for example, theta as a field is clearly going to wrap around on itself, right?
Yes, exactly. It's periodic.
So, I don't know. I guess.
So this is completely analogous to the Higgs, but what happens with the Higgs is that you don't see theta because the global symmetry is gauged. And the thetas are the Goldstone bosons. And when you gauge the global symmetry, the gauge bosons actually, we say, eat the Goldstone bosons, so you don't see them. So this part, if you take away theta, is exactly what you have for the Higgs, if you call Higgs sigma. Yep. Yes. This is a good question. Any other questions? Yep.
So this interaction that you introduced is theta to the 4 times theta star, or plus theta star to the 4?
Yes.
Okay, and this is by hand. Let's say we imagine we have such interaction.
Exactly. So this is just to show you what happens. But there's even, this is going beyond my pay grade, but people argue that there's no such thing as an exact global symmetry in nature, based on arguments with like string theory, quantum gravity, and so on. And so generically, we would expect that global symmetries are explicitly broken, but they can be explicitly broken by small amounts. Just like for the pions, the quark masses are small parameters compared to the QCD scale, and that's why the pions are light. And if you recall, those quark masses, they're protected by a chiral symmetry. So in principle, the quark masses could have been even smaller, because they just come from their coupling to the Higgs. Maybe imagine the quark masses were the same as the electron mass. Then the pions would be even lighter than they are. So we expect such terms. I've written one. It could be many other different, there are many other different possibilities, but you expect them to arise. I should also say there's something, I left a little sort of breadcrumb for anyone who might have spotted this, but this theory still has a Z4 symmetry. If I multiply phi by e to the I pi by 2, then this term remains the same because that's the fourth root of 1. And you see that, so you still have a little bit of a global symmetry left here, which you call a Z4. And you see that, you could call that Z4 here with alpha is pi by 2. And you see that global symmetry preserved here, because if I shift theta by an amount that is pi by 2 times f, then I end up with the exact same potential. So there's a connection. Even when you break the symmetry, you can sort of track, there are theory breadcrumbs that allow you to track what symmetries are left over in the UV and how they constrain the form of the theory in the IR. Okay. So now the question is, an interesting question to ask, I think it's a very interesting question to ask, is could the Higgs be, so we call it when it's got when it's an exact symmetry, we call it a Goldstone boson or a Nambu-Goldstone boson. When it's got some breaking, so it gets a potential, but it's still lighter than the other heavy fields in the theory, we call it a pseudo Nambu-Goldstone boson, which always gets abbreviated to PNGB. So could the Higgs be a PNGB? So we're going to examine this question in a little bit more detail. So this U1 theory isn't going to work because the Higgs field is a doublet and it's complex, so there are 4 degrees of freedom. So what we need is a pattern of spontaneous symmetry breaking which will spit out 4 Goldstone bosons. That's going to be the minimal ingredient that we need. So one possibility would be that the big symmetry, that's the global symmetry in the UV, you could choose, one example would be SU3. Spontaneously broken to, we normally call it H, the remaining symmetry, which is SU2. And we can actually already count, there are theorems about this, but we can just count ourselves. the generators, so SU3, can anyone tell me how many generators, how many symmetries there are, essentially, how many generators there are? Not symmetries, how many generators there are for SU3? 8, right, okay. So here we get 8 generators, and for SU2, 3. So we expect to get NPNGB. I go into this in more detail, much more detail in the notes, by the way, if anyone wants to sort of refresh themselves or look into it a bit further. So the number of pseudo-Goldstone bosons we expect, or Goldstone bosons we expect to get is 8 minus 3, which is 5. We wanted 4, we've got 1 bonus. Fine, I'll take a free particle. For our purposes, it doesn't really matter. So this is one example that could give you a theory for a PNGB like Higgs. It's something that's been studied a lot. And in fact, it's very handy because we know we need to have a remaining SU2 symmetry left over because we're going to gauge it. That's going to become the electroweak gauge group. So this is a nice theory in principle for a pseudo-Goldstone like Higgs. The problem is that this theory itself, well, we've got one extra field, which we need to take care of. But on top of that, this is not enough symmetry to protect you from corrections from the UV theory. Say this occurred because of strongly coupled gauge theory. That's one possibility. You know, the pions emerge when the quarks condense in QCD, and that quark condensation spontaneously breaks SU2 left cross SU2 right down to 1 SU2, which is why you get 3 pions. You got three generators in SU2 left, 3 generators in SU2 right, and 3 generators left over, and the difference is 3, so you get 3 pions. So it could happen via strong coupling like that. But the problem is, another problem is that there's not enough symmetry to protect you against things that would give you large corrections in precision electroweak data. So this theory was actually essentially already ruled out by LEP. But for our purposes, it's simple enough that I can use it to show you some generic or typical features of these classes of models without having to introduce lots of group theory. But there are other examples that work much better. So for instance, if this were SO5 and this were SO4, then you get 4 Goldstone bosons, which is what you want, and you have enough symmetry to protect you against constraints from electroweak symmetry. So if the Higgs were PNGB, it's much more likely to be SO5 to SO4 in the UV than it is to be SU3 to SU2. But for our purposes, we can write things in a way that's familiar, and so we're just going to run with this for a while, run with this for now. We can capture, so here, this was a nice way of parameterizing the degrees of freedom, the different fields, into the Goldstone bosons and the heavy modes, we call them the radial mode. It turns out there's a general procedure for figuring out how to find the nice way of writing things. It's not a legal requirement to write things this way. As I said, you can parameterize your fields however you want, but there's a smart way of doing it. And this smart way is known as the nonlinear representation, other times mentioned with respect to the CCWZ, or if you're American, CCWZ procedure. I'm just going to tell you what it is for the sake of time, but I go through in the notes how to exactly construct this. So the nice way to write our triplet of SU3 in a way that explicitly only contains the Goldstone bosons, so it's not, I can put back in the heavy mode, the sigma if you like, but I don't have to, you don't need it for the low energy physics. And it looks like this. So IH1 sine of H over F over H over F, IH2 sine of H over F over H over F, and F cosine of H over F, where H1 and H2 are the 2 complex fields in the Higgs, right? The Higgs is a doublet, so there's H1 and H2, and this H here, this little h, is just related to H1 and H2 in this way. It's like the length, essentially, of that vector. Okay, so this is just the smart way of writing it, and there's more on this in the notes. Okay, so from this we can now start to extract some of the sort of generic-ish predictions of this theory. So as I said, this SU2, we want to identify it as the gauge group of the electroweak symmetry, the real gauged electroweak symmetry. And it turns out the procedure for seeing how to do that is quite simple. You just gauge the symmetry. So your standard derivative in here or in here just becomes the gauge covariant derivative. So you've got d mu, I'll just write it just for memory, but the usual gauge covariant derivative that you'll be familiar with the gauge fields in it. But these gauge fields are only acting, so it's not a full SU3 gauge field, so these aren't like gluons or something like that. You're just gauging the top corner, the top SU2 corner, so these gauge fields only act on this part here. So if you were to think about these generators, it's all the generators of SU3 that fill out this block here, the 2x2 block, but not these ones. Okay, and so you simply plug that in, have d mu acting on big sigma, all squared, just the usual thing, and you find that the gauge interactions, so for instance, the interaction of the Higgs with two W's or two Z's, looks like this. Once the Higgs gets a VEV, it has the usual form, except it's been modified by an additional factor, which is cosine of V over F. So for instance, the Higgs, you'd have something like whatever is mw squared over V Higgs W plus W minus, and then an additional factor of cosine of H over V. Or sorry, of V over F, where V is the VEV of the Higgs. Okay, so this is something that I think very generically shows up. And so you see that the interactions of the Higgs with two W's, for instance, or the general electroweak gauge bosons, looks standard model-like, and in the limit that F goes to infinity, this argument goes to 0, so this cosine goes to 1, so it would look exactly standard model-like. But when F is not going to infinity, you get a small modification, which is of order V squared over 2F squared. So that's the first thing to note. A second thing to note is that just like with the pions and the electromagnetic gauge interaction, do you remember that the electromagnetic gauge interaction explicitly broke the SO3 symmetry that rotated all the pions amongst each other, because it didn't involve pi 0, it only involved pi 1 and pi 2, which is pi plus and pi minus. And so we've done the same thing here, right? I said, and you were probably pretty suspicious when I said this, I hope you were suspicious when I said this, I said we will just gauge, so we start with this full SU3 symmetry, but we're only going to gauge this block here. And so the interactions you get when you have act on sigma with this covariant derivative have explicitly broken the SU3 symmetry. Just like literally the same, it's just a non-abelian version of what happened with the pions. And so we should expect that because we've explicitly broken the symmetry, that we will get terms in the full theory that look like this. That what I've written before. It's called big H squared. Actually, sorry, that's it there. Lambda squared. So this is putting flesh, just a little bit more flesh on what I wrote down before. I explained that we would expect these things to show up. Here, we have a little bit more detail. We actually know the symmetry, and we actually can see where that explicit symmetry breaking came from. So what are the alternatives? We could have gauged the full SU3 symmetry, and you wouldn't have this problem. But then you wouldn't have any Higgs, because when you spontaneously broke the symmetry, the Goldstone bosons would have been eaten. So that's not an option. And so if the Higgs were like a pion, and this is just like QED, the electromagnetic interaction is for the charged pions, and then this is the way that we would expect explicit symmetry breaking to show up through the gauge interactions, and it's the way we would expect to not be able to arbitrarily increase this mass scale. And indeed, this mass scale, you can associate it with the mass scale of whatever the radial mode was. So it's something like lambda f squared, where lambda could be as large as something like 4 pi squared. There are additional tricks. You can actually soften this. I'll just say it in words. I'm not going to go through it because I don't want to completely run out of time later. But one additional thing you could have done, which is known as the little Higgs class of models, and they're an interesting class of models, is you could have had two sigmas, so two SU3 symmetries, and they're both spontaneously broken. And so that would give you too many gauge bosons, so you would get too many Goldstone bosons, you would get two copies. But if you gauge both of the SU3s with the same gauge group, then, if the two sets of scalars don't talk to each other, then you would get two sets of Goldstones, but one of them would get eaten. But you've not then explicitly broken, where you've only explicitly broken the other SU3 in a way that that both fields need to talk to each other before they realize that they're not actually Goldstone bosons. And so that can delay these corrections to higher loop orders. This is known as the little Higgs class of models. But I'm just going to stick broad brush, so we will stick with these corrections. For the top quarks, how can you introduce a Yukawa interaction? For the tops, it's most important, but everything I will say applies to the other quarks as well. So we do exactly the same thing. We start from a theory that looks SU3 symmetric, and then recall we just deleted the gauge bosons from here. We can do the same thing in the top sector. So we start with a theory that looks SU3 symmetric. So in the Lagrangian, we'll have a term that's like lambda top Q dot sigma, and then top right, where Q here contains the quarks. This is a fermion and a fermion. This is just sigma, the field that you know. And one possibility for what might be going on in nature is if you have this as a three-plet of SU3, and then we break the SU3 symmetry by deleting this field in the same way that we looked like we were gauging the full SU3, but deleted some of the gauge bosons. Yep.
I lost just F. What is F?
F is the scale of spontaneous symmetry breaking. So here, the analogy was with this potential here, F, in here. This is a perturbative model. F could also be, if we think about the analogy with the pions, that's the scale of the quark condensate, which spontaneously breaks the SU2 left cross SU2 right to SU2. So it's the scale of spontaneous symmetry breaking. That's a very good question. Thanks for pointing that out. I should have said it. Okay, so if we do this, then again, we expect the same old thing to happen. So I wrote it before, but I'll just to refresh you, we expect then in the UV theory to get corrections of order from this explicit symmetry breaking, lambda top squared 4 pi squared lambda squared, where lambda is associated with the heavy mass scales in the theory. So for instance, in this example here, like I said, it would be lambda times F squared, which is the mass you saw here. Lambda F squared is the mass of the sigma mode, but there's also a sigma in QCD, so even in strongly coupled scenarios, it's all very similar. So for the gauge scenario, I sketched possibilities for how one might get around these sorts of tunings, or these sorts of contributions. You can play similar games with the quark sector. So one thing you could do is say, well, we're not gauging it now, but why not just make the whole thing SU3 symmetric? So why not just have the full SU3 representation? Because then this whole interaction is completely SU3 symmetric. It can never generate a correction to the Higgs mass or to the Higgs potential, even for that matter. The problem with that is that then you've got an extra massless fermion hanging around, right? To form a Dirac fermion, you pair up this guy with one guy from here. So we'd end up with two light fermions hanging around, whatever we do. So that doesn't work. But then you could say, well, I should have written this lower, but then you could say, well, okay, well, I'm not going to do that. What I'm going to do is just sort of softly break the SU3 symmetry. So I'm going to write this in a fully SU3 symmetric way. And then I'm just going to explicitly break it by writing a term involving this T in a non-SU3 symmetric way. And I'm going to give it a partner, TC, to get a Dirac mass. Then it turns out in this theory, I don't need to make any wishy-washy arguments about, well, they're not wishy-washy in my mind, but some people might think of them as wishy-washy, about what's going on in the UV and so on. In this model, you can actually just explicitly calculate what corrections you get to the Higgs mass, because this here is the only parameter that in this sector that's breaking the SU3 symmetry explicitly. So it must, like I've tried to convince you, it must give a correction to the Higgs mass. And indeed, you can calculate it, and you get a correction to the Higgs mass, which obviously goes like delta m squared in the usual formula. So 3 lambda top squared over 4 pi squared mt squared. Okay, so what did this do in practical terms? We started with something SU3 symmetric, so we want to soften the sensitivity. By making it SU3 symmetric, the Higgs can't get a mass or potential from it. Then we explicitly break it, and we explicitly break it by making this guy here, T, a bit heavier. Right? We give it mass by pairing it up with this partner, but this term here is explicitly breaking the symmetry. And so you really see now very clearly what these sort of quadratic corrections proportional to lambda squared, how they show up, because you can just calculate the corrections of the Higgs mass here, and they scale like this. They have to, because this term explicitly breaks the symmetry. And so, you could try to make, as you try to make this extra colored fermion, the top partner as it's known, heavier and heavier, you get bigger and bigger mass corrections to the Higgs. This is something those of you familiar with supersymmetry will have seen in exactly the same way regarding the mass of the stop squarks, right? Some of you may be familiar with these formulae, but it's a generic phenomenon. It's not particular to SUSY. Okay. Yep.
Something I don't actually get in the way we parameterize the field. There are 4 degrees of freedom, right? So we are parameterizing just 4 out of the 5 goes.
Yes. Yes. Yes, absolutely. Yes.
Why is that this parameterization? For example, for the pions, one parameterize all the boson each together using SU2 or SU3, depending
Yes.
on the flavors.
Yes.
Right? So where's the...
So yes. Very good. The point you're making is a very good point. In fact, that extra goldstone lives along some combination of all 3 here. But in practical terms, so first of all, I don't want you to take this SU3 model too seriously because it's already ruled out. If you did it with SO5 to SO4, you get a similar parameterization. You've just literally got the Higgs doublet. But also, even in this model, you can have additional terms that explicitly break the symmetry, very analogous to this, which make only that goldstone heavy. So you can, for practical purposes, ignore it. Yeah, no, that's a really good way of thinking about it. Sort of like a Ken. So you've got different sources of explicit symmetry breaking, and that's one that you can do to just lift the extra scalar. But that's a great question. Yep.
Sorry to ask this, but I'm a little bit lost. Probably said, but I'm a little bit lost in the motivation. Why do we need all of this? I mean, what does this explain, or what is the motivation for this? I don't understand. I lost the context a little bit.
Yes, sure. So the broad context is the following. We know the standard model has a UV completion because it's not UV complete on its own. It breaks down. So there's some next layer to nature at small distance scales. And as theorists, we're trying to guess what that is and explore what the phenomenological experimental consequences are. And so you have a light, we know from the LHC measurements that next layer is not right next door to the Higgs. It's not at 300 GeV or something. And so there's some mass gap between the electroweak scale and wherever that UV completion shows up. Now, theories that, like for the pions in QCD, but more generally, theories where scalars are pseudo-Goldstone bosons are scenarios where you can have a mass gap like that. You can have a gap between the mass of the scalar field and the scale at which the UV completion kicks in. Essentially, in this example, it's because this lambda tilde can be as small as you like, and then that's what generates the mass for this scalar. So this is a class of theories where you can have a mass gap. And so we have this question, we have this thing that we know that the standard model needs to be UV completed at some scale, but also the LHC is telling us that there's a mass gap. So right now we're exploring, could that mass gap be because the Higgs is like one of these fields? It's like a pion. That's the motivation. But thanks for asking that. I think probably there's more than one of you who's thinking that. Any other questions? Okie doke. So let's return to this question of fine-tuning. So as I've said, there's no free lunch, right? These things are showing up in exactly the way I said they would. You can see it a bit more explicitly now because we have an explicit model, but there it is. And we can also, in these theories, start to, because we have, at least structurally speaking, we have a picture for what the UV completion might be, we can actually start to make calculations. And as I said, you know, in any scenario where you have a low energy effective field theory description of the light stuff and then a UV completion, then at least in the scenarios we've seen in nature, you can calculate the properties of the IR theory from within the UV theory. Should be calculable. At least that's every example we've had until now has been of that nature. And so we should be able to calculate things, you know, not just talk about it, but we should be able to calculate the Higgs mass, and we should be able to calculate another property concerning the Higgs sector, which is the Higgs VEV. So there's two parameters, right, that you need to get out right. You need to get the Higgs VEV, we've measured it, essentially, you know, arguably we measured it in muon decay, thanks to one of Fermi's other great theoretical achievements through the Fermi interaction, and the Higgs mass. So we want to be able to calculate both of these things. And in this class of models, it turns out that you can. You know, if the UV completion is strongly coupled, you would need a computer. You would need to do lattice gauge theory or something to calculate it, just in literally the same way that we calculate the pion mass and decay constant in lattice QCD. So it's not, there's no in principle obstruction. If it were some perturbative model where this chordic coupling lambda is small enough that you can use perturbation theory, then you could even calculate it there. But in any case, whichever way, whatever's going on, you can calculate it in principle, and you get corrections of the Higgs potential, which look like the following. I'm going to parameterize it in a particular way to make life easy. F squared lambda squared, all multiplying. I'm going to write minus r sine squared h over v. Sorry, v over f. No, h over v. H over f, sorry. Plus sine to the 4 h over f. So these tend to be the leading types of corrections that contributions to the potential that you expect to get. The sine squared, actually, you can already see that that was going to come up. So everything here, why sine and trigonometric functions? It's because of these terms here. Essentially, you can integrate out, you know, calculate these corrections, and coming, for instance, primarily from the top sector, and you get things that are functions of this thing, which are electroweak invariants. So you expect to only see things like that are gauge invariants, so h or sine of h over f or cosine of h over f. Why sine squared and sine to the 4? Because actually, just by doing, again, a Spurian analysis, you can see that this parameter here enjoys a spurious Z2 symmetry, right? I could multiply tr goes to minus tr, and lambda t goes to minus t. And this theory remains the same. So that means that if I integrate out, you know, if I'm sort of calculating the effects of the top sector, unless I see a TR, I expect to see lambda t squared. And lambda t comes along for the ride with the sign of Higgs over f, so you get things like this. Okay, so from here we can just minimize this potential. dV by d Higgs is 0, and find the minimum. When you do this, you can see, it's a very straightforward exercise. You can see that when you minimize it, that if you want to get the VEV of the Higgs to be V, which is what we observe, right? We've measured the electroweak breaking VEV. Then you need to have, by setting V prime equals 0, dV by dH 0, you see that R has to be something like 2 sines, not something like, in this case it is, 2 sine squared V over F. If R is 2 sine squared V over F, then the minimum of this potential is at V for the Higgs. But when you do these calculations, you generically find that this coefficient and the coefficient of this term, packaged in terms of beta here, are both order 1 numbers. But we also saw here that the modifications of the Higgs couplings to vectors, for instance, is cosine of V over F. So that's 1 minus V squared over F squared. sorry, v squared over 2f squared. So if the Higgs is going to be standard model-like, you know, we've measured the Higgs coupling to Z's and W's pretty well. It's of order, at the moment, the 7% level. If the Higgs is going to be standard model-like, then we need V over F to be a small number. But if we need V over F to be a small number, then R had better be a small number. And so that this theory is starting to look tuned, right? The coefficients of this thing and this thing, you expect them to be sort of similar, order 1 numbers. Yet, you need this thing to be actually very small if you're going to get small V over F and a standard model-like set of Higgs interactions. And so this is known as V over F tuning. We can quantify it. You usually see a big delta that quantifies the tuning, which in this case is 1/2 F squared over V squared. So big delta means big tuning. So if V over F is small and F over V is big. So for a more and more standard model like Higgs, you have more and more tuning. Or sometimes we write it 1 over delta, and then it's a small number. Say if 1 over delta was 0.01, then you'd say there's 1% tuning. But similarly, we can connect this. You saw that the corrections from this, I'll just write them out. You know, cosine of V over F is 1 minus V squared over 2F squared. So this is the correction. You'd have 1 for the standard model. This is the correction to the Higgs interaction with the vector bosons. So you see that there's a direct connection here between the fine tuning, if we say the mod, the fine tuning, and the Higgs couplings. It goes like this: 1 over 4 delta C Higgs vector vector. So in this class of theories, if the Higgs were like a pion, which is a logical possibility, then the more and more standard model-like the Higgs becomes, you know, if we have constraints at the 7% level, then at the 7% level it's standard model-like. The more and more standard model-like it becomes, the more and more fine-tuned the theory would ultimately have to become. And so for me at least, you know, you can interpret it how you like, but for me, if the theory is becoming more and more fine-tuned, it's looking more and more like that logical possibility is probably not what is actually going on in nature, okay? Also, you shouldn't, the numbers for fine-tuning, I wouldn't worry about them too much. Quantifying fine-tuning is a bit of a tricky, it's a bit tricky conceptually, but nonetheless, you should be worried if your fine-tuning is like the 1% level, and you're trying to guess at what's happening in nature, and you're finding that in your guess, you need to fine-tune some numbers to the 1% level, then probably that's saying that that's not what's going on. Okay, so what about high Lumi? What could happen at high Lumi? There's some very interesting prospects at high Lumi. There are three basic areas that I want to discuss: Higgs couplings, searches for vector resonances, and searches for colored resonances. So at high Lumi, currently at the LHC, present constraints on Higgs couplings, to the vectors particularly, are about delta C HVV, we'll call it, is at the level of, say, 7%. I'm assuming here, so this is like the error on the central value. I'm assuming that the central value is standard model. Like here, of course, it's not actually in the different, you know, in Atlas and CMS. There's a slight deviation. Maybe that's a sign of new physics. Maybe not, but that's the sort of the accuracy that we have. So at high Lumi, what would we expect? So this is LHC. Delta high Lumi LHC of CHVV. Again, anyone who is careful with their statistics is going to want to throw their laptop at me, but I would say it's probably going to be about something like 7 times the square root of 140. That's the present analyses, the present integrated luminosity you see at analyses, over 3,000. And this is about 1.5%. So this is assuming that there's not significant systematics here affecting these measurements. If there are significant systematics, you would not do this well. But it turns out you can go and search for projections for high luminosity LHC and Higgs couplings, and it turns out to be about this. Which means that then, at present, this corresponds to, so we saw this is what the tuning here, there's a 1 over 4 delta CHVV. So the present tuning from Higgs couplings is in these models is around the 30% level. But if we didn't see, so maybe there's some deviation in the Higgs couplings to vectors, and then it will maybe persist, and then we'll get some evidence for new physics. But if that didn't happen, if we had a standard model central value and a 1.5% accuracy precision measurement, then this would correspond in the future to something like a 6% tuning. So I would say that the possibility that the Higgs is PNGB-like, at least in the most basic class of models, would be at that point looking, I would say, unlikely. Maybe some diehard people who like these models would hold on to it, but at that point I would be willing, for this class of models, to chuck it in the bin. What about direct searches of particles? So there's one class of particles that you expect to show up in these sorts of models, which is extra vector resonances. I'm not going to go into much detail about why you expect to see them, but you can understand it by analogy. So for QE, you get the pions, but there are also the Goldstone bosons, or the PNGBs, sorry. But you also get composites made up of the same quark pairs, but which are vectors, which is like the rho meson, essentially. And so if you had a PNGB-like Higgs and the UV completion were sort of QCD-like, you would generically expect things like the rho meson to show up, but they're the rho meson of that sector. They're not at 750 MeV. And so generically in these models, you expect such vectors to show up. And they would couple typically to quarks and leptons because the Higgs, yep.
Does this hold only for composite Higgs scenarios, or it's general? Because the vector resonances are just another way to arrange the quarks, right?
Yes.
And so we have to assume that the Higgs is composite to expect these vector resonances, or it's more general?
It's a great question. And so my answer is I'm not entirely certain of what my answer should be, but for sure when it's composite, when it's strongly coupled, you really expect them. And you can write models that have this structure of symmetry breaking, where it's PNGB-like, which are not strongly coupled, like models that involve SUSY, but have, the Higgs is coming out like a PNGB, which don't have the vector resonances. So yes, you sort of typically expect them if it's composite, probably not necessarily if it's a weakly coupled sort of perturbative UV completion. Okay, and so they would couple to things like quarks and leptons, and you could get things like dilepton resonances, for instance, and there are very strong limits on these. Can you show figure 6? There are very strong limits on this. And as I said yesterday, it's very hard to, with pen and paper, unless you've sort of hard-coded, PDFs into your brains, it's very hard to estimate how the mass reach will change. Say this is the cross-section. It's falling as a function of mass because the cross-section tends to depend on mass like 1 over mass squared, but also the PDFs play a role. So if we want to estimate what happens at high luminosity LHC, it's very hard with pen and paper, because you're essentially, if this is the present limit on some mass scale, you need to estimate how much this is dropped to compensate for the extra precision from the luminosity to estimate the new mass scale. But in the notes, I've given you a link. It's not very clear, but if you look at it, you can see it's a slightly different color, to an online tool called Collider Reach. Has anyone seen this already in the notes? Probably not. So you can click on it in the text, and this enables you, it's a very fun website, to estimate how the mass range for things like vector resonances will change in future. Just be careful, if you click on the links, your browser might automatically put an S for HTTPS in the address, then it won't work. So you need to delete that S. I don't know if that's like dangerous for security or something like this, but I know the people who made the website, and They're very trustworthy people, so I'm sure the website's fine. Or maybe it's not. I don't know. Am I like introducing legal liability here or something? But anyway, so you can see how that how things will evolve for these vector resonances by using that tool. But already you can see that the current limits from CMS with 100, 140-ish inverse femtobarns are pretty strong, right? These vector resonances, the direct searches looking for literally a bump in the data in dileptons is super high, right? You're talking multiple TeVs. And so if you recall, the rho meson wasn't too far away from the compositeness scale, or the QCD scale. And so if these vector resonances are above the few TeV mark, then you would expect the compositeness scale is probably above the few TeV mark, which is putting indirect pressure on the questions about how much fine-tuning there is. And also there are even for weakly coupled scenarios, so G star sort of parameterizes how composite the UV completion is, how strongly coupled. If these resonances were not very strongly coupled with, say, G star less than 1, then they could, you can rule them out to even higher masses that are beyond, essentially, because of the PDFs that are essentially beyond the kinematic reach of the LHC, because they would have indirect effects on the tails of the dilepton distribution. This is something we'll talk about later this afternoon. Essentially, this is the standard model prediction for essentially d sigma by dE as a function of energy. This would be the standard model prediction, and this would give corrections that look like this. And if you have high precision predictions for your standard model rate, you can constrain such corrections. And so you see that this is already putting pressure. And finally, we can have a break if you want, but I just want to mention the colored resonances. As I said, as I showed you, you expect to have colored fermions to come along for the ride. We call them top partners. And these colored resonances are also something that would show up at the LHC. Yes, if you want, for any mass point here, for the direct searches, not for this indirect search, but for these direct searches, to estimate how this scales with high luminosity LHC, you could just pick a parameter point, pick a mass, for instance, and use collider reach, and you will see how that should, to a reasonable approximation, how that should change for high luminosity LHC. For the colored resonances, I charged under QCD. The present limits are around 1.5 TeV, which is big. And so already we're getting corrections to the Higgs mass squared, which are too big and essentially correspond to having to fine tune for the mass, not the VEV, at the 10% level. And for high lumi, can you scroll forward to figure 7? For high lumi, you can see that these searches, it's where this is the theory, the model prediction, and this is the expected limits. And so you see it crosses over at about 1.8 TeV. So at high lumi, we expect 1.8 TeV, which would be even more tuned, but not wildly more tuned. So my argument at the moment, I was saying this to Simon last night, is that actually the big story for how tuned this class of theories is, as we go to high lumi, in my view, it's not going to be driven anymore, even though it was driven in the past by searches for colored particles, but it's really going to be driven by a big shift in the precision that we can measure Higgs couplings for this sort of broad class of models. Okay, so I guess I should stop, or I'm going to take a vote. Who feels like they need a break? Everyone, not me, but okay. So let's take a short break, like 5 minutes, and we will start again at 10 past on the dot. So if you haven't got your coffee by then keep waiting for your coffee and miss some physics, or come back. Okay, so let's get started. So what I want to do, so the point of the last, the point of the last part of this lecture was to, one, introduce you to a sort of popular class of models when people think about what could be going on in the Higgs sector, and also their sort of generic collider signatures, new colored fermions, and so on. Also to concepts which are more global than that, which apply to theories beyond just PNGB-like Higgs models. So for instance, that connection between new colored particles and questions of fine-tuning and Higgs coupling measurements and questions of fine-tuning is also pretty much, you know, to a first approximation, pretty much the same for supersymmetry. Okay, so the point was to sort of familiarize you guys with some of those broader aspects. But now, in this lecture, I want to talk about something more exotic, which I think is very interesting and shows that when trying to ask this question about what's going on in the Higgs sector, one can be driven towards some very interesting collider signatures, which are particularly interesting for Halloumi, which is the topic of, well, BSM at Halloumi is the topic of these lectures. And so this class of models is known as the twin Higgs class of models. In my notes, there's all of the relevant references. That absolves me from having to provide you with references now. So the twin Higgs class of models is a class of models that is PNGB-like. So all of that technology that you grappled with in the last lecture will be useful for this lecture. But it was developed in a sense, it was developed actually before the LHC switched on. It was essentially developed, the main conceptual nuts and bolts, in 2006. And the idea was, you know, could it be that in theories where the Higgs mass and vacuum expectation value are not fine-tuned, could it be that you don't necessarily expect new, like, colored QCD particles, charged particles, to show up at the LHC? And the authors of this work found that was indeed possible, but in a very peculiar and interesting way. And then when the LHC, so this paper was sort of largely forgotten. There was actually a few papers they wrote was sort of largely forgotten. It remained as a bit of a curiosity. And then when the LHC turned on and didn't discover stop squarks or fermionic QCD charged particles, then people started to revisit some of the assumptions that had been made, and then these papers were sort of, in some sense, rediscovered. A lot of people started paying more attention to them. Okay, so now I want to go through the structure of these models and also the sort of signatures that show up. So we're going to use exactly the same technology, but ultimately with a twist. So we will start with a global SU4 symmetry, which is just like SU3, but with one more index. We will write our Higgs field, big Higgs, as a fourplet. So there are 4 complex fields. And ultimately, we're not going to do this right away. We're going to identify this as the standard model Higgs. I'm going to call it Higgs A for reasons that will become obvious later. And this one here as a copy Higgs. So this is a model. You can see where this is going. It's all in the name. So there will be 2 Higgs doublets. But for now, let's package everything like it's just an SU4 fourplet. Okay, so we can write down a standard, the same old potential, a Mexican hat potential, and do the usual trick of spontaneous symmetry breaking. So we would have something like this, where big H is literally this thing with all 4, plus lambda over 2h to the 4. So standard Mexican hat, Higgs-like potential, something you're now very familiar with. But there's a negative mass squared, and so this whole fourplet somewhere along here will get a vacuum expectation value. We'll call that F, as usual. And we will get a bunch of Goldstone bosons, because this is SU4 symmetric. So we will have SU4 spontaneously broken to SU3. Can anyone tell me how many Goldstone bosons we get? Yes, very fast. Yeah, so we get 7 Goldstone bosons, or Nambu Goldstone bosons. Okay, so that's what we expect to happen. We can also write this in a, now if we now I'm going to just change notation, but it's exactly the same potential. You can see here that this is clearly SU4 symmetric, but I'm going to write it equivalently in terms of this pair and this pair, like this. HA squared plus HB squared minus F squared over 2, all squared. So it's exactly the same scalar potential to all intents and purposes. There's an overall constant which is different, but that's unphysical anyway. And so you can see here that this potential here, it's just the same thing. There's an SU4 symmetry. So when, at the minimum of this Mexican app potential, some combination of these fields is going to get the VEV F. You might call it this one, you know, F sine theta, and that one F cosine theta or something like this. But they will get the VEV F, and you will get 7 Goldstone bosons spat out. Okay. So these are the main building blocks. Now I want to discuss, probably I'll need a whole board, so I'll do it here, I'll keep that up there, gauge interactions. So what we're going to do is very similar to what we did for the last SU3 example. We're going to explicitly break the global symmetry by gauging a subgroup of the global symmetry. But what we're going to do is gauge a different subgroup. We're going to gauge the electroweak subgroup, but you see that we've got four columns and 4 rows. And so we're going to gauge 2 SU2 subgroups. So this would be, you know, sigma A, big A, no, A, do that, little a, and this guy's big A, and this would be sigma A, W A, big B. So the A sector and the B sector you can see in there. So this would be the set of generators and gauge fields that goes into the covariant derivative. And so we can incorporate that by adding to the potential the kinetic terms, L kinetic, which would take the form of d mu Higgs A, all squared, plus d mu Higgs B, all squared. And the gauge fields A and B are different, right? They're not talking to each other. So this is like, we've got 2, you know, we're working in an SU4 language, but you can see where I'm going here is that we've got copies of things in SU2 language. We've got one Higgs doublet and a copy Higgs doublet. We've got one full electroweak gauge group and a copy full electroweak gauge group. And what else we find now is that when one of these fields gets a vacuum expectation value, 3 of the 7 Goldstone bosons will be eaten because you're going to break one linear combination of the gauge symmetries. So the 7 Goldstone bosons now will give us 4, there will be PNGBs, as you'll see, so 3 which are eaten. So for now, I'll come back to this, but for now, let's pretend all of the breaking is in the B sector. So Higgs B gets the VEV F, or F over square root 2, depending on how you want to choose your normalization. And so that would then spontaneously break the SU4 symmetry. You'd get your 7 Goldstone bosons, but because of this gauging, this term here means that the 3 Goldstone bosons that are coming from the Higgs B field get eaten to become the longitudinal modes of the B field electroweak gauge bosons. Okay, so this is all sort of like a twist on the original picture that I've already shown you. But where things get really interesting is when we start to talk about the explicit symmetry breaking and contributions to the Higgs potential. Because we can do exactly the same sort of formula that I'm sure you're really tired of seeing me write now, because we would expect to get corrections to the Higgs mass, or the Higgs potential, let's write it as, which scale like this, GA squared over 4 pi all squared, the cutoff squared, Higgs A squared. Right, this is the exact same thing, because by gauging this subgroup here, we've explicitly, of the global symmetry, we've explicitly broken the global symmetry, so it's no longer protecting us from generating a potential. However, how that breaking arrives in the potential is very clear, because if we were to set the gauge coupling to 0, then we haven't explicitly broken the symmetry anymore. So it has to be proportional in some way to the gauge coupling, or gauge coupling squared, more precisely. But also this happens in the B sector. So this is nothing new to you at this stage. GB squared 4b, 4 pi all squared, lambda b squared, Higgs b squared. And here, lambda b and lambda a are the cutoff, the UV scale. So that would be something like, you know, in a perturbative model, something like lambda f squared, for instance. But now you see the trick. Because if these were really twin sectors, you know, really identical twin sectors, then the cutoff in both sectors would be the same. So let's just call it big lambda. And the gauge couplings would be the same. If they're really twinned, then one way of saying this is that there's an exchange symmetry between both sectors. If you swap the fields in both sectors, the theory remains the same. And so the two electroweak gauge couplings would be the same. All looks, you know, pretty uninteresting so far, except for the fact that all of a sudden you would realize that this is now SU4 symmetric. This, we can write it like this, over 4 pi squared, lambda squared, Higgs A squared, plus Higgs B squared. But if this is SU4 symmetric, then it respects the global symmetry. So there's no way it can generate a mass for your Goldstone bosons. I could reabsorb this into the definition of F there in that top term. Does anyone not understand this? Because this is the crucial trick of the twin Higgs. So if there are any questions, shout out and I can go over it again or phrase things differently. No? Okay, great. Yep, good. Yes.
And this term as well is what we say.
Yes.
And let's say this is basically the same, almost the same as the potential, so we can shift potential quite.
Yes. Yes, exactly. So this thing here will not generate a potential for your PNGBs, even though it was generated by terms that explicitly broke the global symmetry. And we call this one bit of jargon we use to describe this is we say that there's an accidental symmetry. If you have at the level of the field squared, so we say the quadratic terms, if at the level of the field squared you have only an exchange symmetry, then the only thing that you can write down is actually SU4 symmetric by accident. Because if I've got an exchange symmetry, I can only write something at the quadratic level which looks like this. But already it's SU4 symmetric. And so this is the neat trick of the twin Higgs. And so our explicit symmetry breaking here will not generate the usual sensitivity to the UV scale for the Higgs boson, because the Goldstone boson is contained in here. In fact, you could even see it more explicitly, because if you go to unitary gauge and look at all the things that are eaten, then once the Higgs gets a VEV, you could write this is going to be very sloppy here, okay? But you could write Higgs A, the whole field, let's call it sigma again, as like sine Higgs over F, cosine Higgs over F, with say some zeros, and F in front. And this would be Higgs A and this is Higgs B, so you plug that in here and you get sine squared plus cosine squared, which is 1. It doesn't depend on Higgs anymore. That's one way of sloppy but quick way of seeing it. Okay, but that exchange symmetry is not sufficient to protect you entirely, because the exchange symmetry, if you write it at the quadratic level, it automatically guarantees you SU4 symmetry, but there's nothing to stop you getting terms at the quartic level, so say Higgs to the 4, which would show up and break the symmetry. So I'm just going to continue down below here. Actually, no. Let me leave that on there. And continue over here. There's nothing to stop you getting terms at the quartic level which explicitly break the symmetry, and indeed that's what happens. So you get something like delta v to the 4, which is going like g to the 4 over 16 pi squared. This is a marginal operator, so you expect to have logs, and you do get logs. You get something like m squared over lambda squared, where m would be, say, the mass of the radial mode, so m squared would be lambda f squared, and big lambda would be the cutoff. Oh, no, sorry. This would be like the mass of the gauge bosons, for instance. And a term that goes like Higgs A to the 4 plus Higgs B to the 4. And you can see that this term here is not SU4 symmetric. It's exchange symmetric, but not SU4 symmetric. If it was SU4 symmetric, it'd be something like this, Higgs A squared plus Higgs B squared, all squared. So this explicitly breaks the SU4 symmetry, and so it will generate a contribution to the mass of the Higgs and the Goldstone bosons more generally. So delta m squared of P n G B is scaling like g to the 4 f squared over 16 pi squared, where f is the scale in there of spontaneous symmetry breaking, times some logarithm, which is a ratio of scales. And so what we get is that we've softened the contributions to the Higgs mass. You see there's 4 gauge couplings in here, not 2, like in the more vanilla PNGB like Higgs model. And you get you could rewrite this as G squared MWB. That's the mass scale. So G times F is the mass scale of the twin gauge bosons. So MWB squared over a loop factor, 4 pi squared. And so you have sensitivity to the UV scale, but it's been softened. These are smaller numbers. As to be compared with something that was like G squared times big lambda squared, which was could be something like 4 pi f squared. Okay, what happens in the let me see, what happens in the no, sorry. Yes, we can also, sorry, I will just finish up on one additional point. I'm just going to sketch through it for the sake of time, but you've noticed that this theory is exactly exchange symmetric. And so as I've written it, I was actually a little bit dishonest, because I pretended we could have some VEV in the A direction to break electroweak symmetry breaking and some VEV in the B direction. But that's not strictly the case. Because it's exchange symmetric, you would either have both VEVs equal, so both VEVs are something like f over square root 2, and then you've gained nothing because your twin sector and standard model sector are at the same mass scale. You've got no separation of scales. Or you could have that the Higgs VEV VA is 0 and the other VEV is f. But we do have electroweak symmetry breaking. The Higgs VEV is not 0. And so it turns out that the only way to get the VEVs to be different is to introduce, or if this were described nature, there would have to be some additional source of explicit symmetry breaking. And to make the Higgs VEVs different and one much smaller than the other, then you have to do exactly the same sort of fine-tuning that you had to do in the old model that I wrote down. So the fine-tuning turns out to scale in the same way. It goes like it goes like f squared over v squared. And so to get standard, and you get the same sort of corrections to the Higgs couplings to vectors as we had before. And so the more standard model-like the Higgs couplings look, the more fine-tuning you have to do, at least in this sort of basic incarnation of the model. So that bit is the same as the other PNGB-like Higgs story that I wrote. There's actually, arguably, there's a factor 2 difference. So the fine-tuning is a little bit, for the same small corrections to the Higgs coupling to ZZ, for instance, you can do better by a factor of order 2 in the fine tuning, but still that's not great when your Higgs couplings are at standard model like at the 7% level. Yes?
Sorry, but the UGA was this model because the H coupling doesn't contribute to the mass.
Yes.
And the UGA was
About to do it. Yes. Thanks. Yep.
regarding these models and the amount of fine tuning there, is, for example, the measure of the discrepancy of the coupling with the vectors the only parameter where we can like, measure this discrepancy, or are there like any other couplings that might constrain and help us understand whether a composite Higgs is a possibility or not?
Yes. It's a really, really good question. So let's not talk about twin for a second, go back to the older model, just the standard one where you've colored top partners and things like that. So the correction that I showed you to the vectors is sort of pretty universal. Any type of model that you write down of that general structure, PNGB like Higgs, will give those corrections. And in fact, that's why you're seeing this here. Whether or not those corrections are tied to fine tuning is a little bit more involved. So there are models where they're not tied to fine tuning, even the ZZ couplings. I can tell you about that after the lecture if you're interested. But you do also expect other Higgs couplings to get modified. For instance, the Higgs couplings to fermions are modified by corrections that scale in the same way, like v squared over f squared, but the coefficients of those corrections depend on how the Yukawa couplings arise in the full UV theory. So we say they're model dependent. They're never like 0. So it's like v squared over f squared multiplied by some number, which is like a half or 1 or 2 or maybe 3 or something like this. So indeed, in this class of models, you do expect to observe essentially universal corrections of the Higgs couplings to vectors. So that's one way of search, like I've mentioned, that's one way of searching for could the Higgs be a PNGB or could it be composite, moreover. And then you do expect different modifications to the fermion couplings as well. And by measuring, if you had a perfect machine and you could measure those deviations perfectly, you could start to tell more details about how the Yukawa interactions arose. So that aspect is model dependent, but you do expect to see that as well. And in addition, the things I mentioned, actually directly producing the fermionic top partners, the vector resonances, and things like this. So that's the sort of the collage of effects, BSM effects that you expect to show up.
So these kind of models are at the moment not ruled out, because I only
No.
know one that is the Technicolor, and that was somehow ruled out.
Yeah, so Technicolor, you wouldn't have had a Higgs at all. In Technicolor, the breaking of the electroweak symmetry, as it was initially written down, the sands have shifted as to what people mean when they say Technicolor nowadays, but in the original models, it was really like QCD. So here's an interesting thing for you. Imagine you had QCD, but not the electroweak gauge group. The quark condensation would have spontaneously broken SU2 gauge and U1 hypercharge. In fact, the QQ bar pair that condenses has the same quantum numbers as the Higgs. And so it would have been the quark condensation that spontaneously broke the gauge symmetries, and the pions would have been eaten to become the longitudinal modes of the W and Z. And that's what Technicolor is. Technicolor wanted to do that for the electroweak sector. So at higher energies, some strongly coupled theory would have some quarks, they condense, and spontaneously break the electroweak gauge symmetry. And so that wouldn't have had a light Higgs boson. It would have had a radial mode, this sigma that I discussed, just very analogous to actually the sigma in the sigma meson. But it would have been pretty heavy, like TeV, around the TeV-ish scale or thereabouts. And it would have been a very strongly coupled theory. One could have implementations potentially of Technicolor where that sigma meson happens to be light and sort of looks a bit Higgs-ish, but it's hard. So I would say there. I think it's okay to say ruled out for Technicolor, in my view. For things like supersymmetry or these composite Higgs models, they're getting more and more tuned, and it depends what your comfort level is, in the sense that, we're trying, model building isn't some cottage industry where you just churn out papers of models. You're trying to figure out how nature works. And so if you're working on a theory that you think might be what's actually going on in nature, but you see that within that theory, nature would have had to fine-tune couplings to like the 1% level then, or say the 10% level even then, I think one starts to be suspicious that that model may not describe nature. But I would never say ruled out. Ruled out would then be, is it then like a subjective question? Any other questions? No, okay, great. Yukawa interactions. So, yes, sorry, I jumped the gun talking about the tuning already here without talking about the top sector, but we'll talk about the top sector now. So indeed, by the way, the reason I write up my notes is because my handwriting is so bad that having notes for you to look at guarantees that you can actually read what I want to say. Okay, so as you recall, the couplings to the tops before look like this. So now we're going to do the twin version. So we've got A sector, which would be the standard model sector, Higgs A, QA, UCA. So there's the Yukawa interaction. And as we know, this gives a correction of the potential, which is going to go like lambda A squared, there's probably a 3 and a 4 pi squared, and a cutoff squared, Higgs A squared. So you can probably anticipate what's going to happen in the twin model. You have twin quarks. Higgs B, QB, UCB. And we'll assume, like with the gauge sector, that there's some exchange symmetry. So these Yukawas, you'll notice that I use lambda for almost everything. I'm sorry about that, but it means I don't have to come up with a different Greek letter each time. So this is called lambda top. This is, we're talking about the top Yukawa. Then you get corrections to the potential that look like this. And once again, you see that this is actually, thanks to the exchange symmetry, is actually SU2 symmetric. So it works in the same way as the gauge sector. So these corrections would be there and in principle calculable, but they would be exchange symmetric. So here, they don't actually generate a potential for the Goldstone bosons. On the other hand, just like with the gauge sector, you do get quartic interactions. You get quartic interactions generated. They would look something like this, lambda top squared over 4 pi squared, some log of mass, ratio of mass scales cut off to, for instance, the lambda top times F. And then Higgs A to the 4 plus Higgs B to the 4. And once again, you see that that is not no longer SU4 symmetric. And so you get a correction now in the end of the day to the Higgs mass. It's called delta M Higgs squared, which gives like 3 lambda top squared over 4 pi squared log of some ratio of scales times essentially, so F times lambda top is the twin sector top mass. If you recall, F is just the VEV, so Higgs A has the VEV V, Higgs B has the VEV, or Higgs B squared has the VEV F squared minus V squared, which is essentially F. So F is lambda top times F is actually the mass of the top quark in the twin sector. So this goes like M twin top. Let's call it MTB squared. So now you see something really interesting, right? Because if you recall from the PNGB model, where you had the colored top partner, and then remember we explicitly broke the SU3 symmetry to raise the mass of that top partner because we haven't seen it. And then we got corrections to the Higgs mass, which looked like this. But this thing here was something that's colored, and so we hadn't seen it, and we had to push it up, and that increased the fine-tuning of the Higgs mass squared. But now this thing here that's playing exactly the same role has no QCD charge. As far as the standard model is gauge group is concerned, it's invisible. So the fact that it hasn't shown up at the LHC so far is not a big problem, right? It could be sitting at 6 or 600 GeV or something like this, and who cares? Because it's not being produced by gluons. If we had a twin LHC, we could collide twin protons, there would be twin gluons, and we would produce the twin top quarks. But here, it's invisible as far as we're concerned. And so, this is as a result of the fact that you don't get, that the correction scale in this way is a result essentially of the SU4 symmetry, and the fact that an exchange symmetry enforces SU4 symmetry at the quadratic level by accident. you can see this, so I'm just going to say you can see this in a number of ways. As I wrote the way that you don't get corrections proportional to big lambda squared. One way of seeing it was to use the nonlinear representation. You get sine squared plus cosine squared is just 1. It's not a function of the Higgs. Another way you can see it is you can actually just work with this model with Higgs A and Higgs B and do something very sloppy and estimate the size of your quadratic corrections. You've got like a Higgs A here and a Higgs A here, lambda top here, lambda top here. You've got tops running in the loop, TA, the visible sector tops. But also once Higgs B gets a VEV, you get a cross term between the Higgses. So you also get you can estimate very sloppily the sensitivity to the UV scales by using something like a Pauli. I really hate doing this, but I felt like I should say it, like a Pauli-Villars regulator or something. That is not telling you that those are what the corrections are from the UV, but it enables you to sort of estimate what the corrections from the UV might be. And you can perform exactly the same exercise. And you see here, you've got a diagram with Higgs A, Higgs B. Got a cross term in here. This vertex, you can calculate it from that scalar potential right at the top. And it's just lambda F, where lambda is the chordic coupling in the scalar potential. The mass of Higgs B in here is lambda F squared. So you get from this propagator, if the momentum exchange is small, you've got 1 over lambda F squared. And then you've got twin top quarks in here. You've got a lambda top, and you've got the top mass is in the numerator, so let's call it here, the twin top mass, but the twin top mass is lambda top F. And if you stare carefully enough, you see you've got a quadratic sensitivity to the cutoff in here, in this Feynman diagram, loop diagram. I've got quadratic sensitivity in here, but this diagram is exactly minus that diagram. Because here you've got a lambda F, 1 over lambda F squared, and a lambda top in here, and a lambda top F for the mass insertion here. And this, if you're careful with your signs, has an overall minus sign compared to that. So that's one way of seeing the cancellation of quadratic divergences. Personally, it's sort of nice to see how these factors all work out. Personally, I think this is a really bad way of thinking about this model, because it's much more clean to just think about the symmetries and the fact that this is SU4 symmetric, so cannot generate a mass for the Goldstone boson. But if you like Feynman diagrams, then that's one way you can see it. Okay, so I'm going to finish up by talking about the phenomenology of these models, which is very, very cool. So I'll do it on this side, I think. So as you would expect, these models are very peculiar in terms of phenomenology because you have the standard model and a copy, and that copy has its own QCD, its own electroweight gauge group, and so on, its own quarks, its own leptons. But the only connection between the two sectors, the only way that they talk to each other is through this cross term in that Higgs potential, so the two Higgses. That's the only way these two sectors see each other. So it's very peculiar in that respect. And the collider phenomenology is entirely driven by that fact. So there are a number of experimental signatures that are interesting to look for. The first concerns the Higgs couplings. So you've got the Higgs couplings to, for instance, tops, and everything else is modified by a factor of hang on, I've got the wrong one. By a factor of 1 minus v squared over 2f squared. Here, so this is the little Higgs, the standard model Higgs, and the tops. But also the heavy Higgs, I'll call it big H, has a coupling to tops because the heavy Higgs and the standard model Higgs have mixed with each other by a mixing angle that is v over f. And so it has inherited couplings to the standard model top sector, which look like lambda top 1 minus lambda top v over f. So you have a Higgs and a heavy Higgs. The Higgs couplings are modified by an amount that's proportional essentially to cosine v over f. The heavy Higgs is a new neutral scalar beyond the standard model that has Higgs-like couplings to standard model states, but they're suppressed by v over f. And so you could produce this heavy Higgs, for instance, via gluon fusion, something like that. And it could decay to things like pairs of Higgs bosons. So you could search for things like di-Higgs resonances and so on. But where the experimental signatures get really, really interesting, which follows from this, is that the light Higgs, just in analogy with this, the light Higgs has inherited couplings to, for instance, the twin sector particles by a factor proportional to V over F. So for instance, for tops, you've got something like lambda top V over F. And this is the twin sector, so let me call it twin here. And that twin sector has its own QCD and so on. And so what can happen is that you could produce, for instance, a Higgs at the LHC. The best way to do it is via gluon fusion. That Higgs could occasionally decay through a twin top loop. So you see that there's a V over F suppression in here. Through a twin top loop into twin gluons. These twin gluons would twin hadronize, so you'd get twin mesons and things like this. Or if the quarks, because F is large, the quarks in the twin sector can be actually heavier than the QCD scale, so then what you would expect to hadronize into is actually twin glue balls. These twin glue balls would propagate for some time, and then eventually they would decay, but the only thing left for them to decay into is back through the Higgs portal into standard model states. So we usually call these twin glue balls G0. And they would have, they're long-lived, so they can have displaced decays, and so then you can get things like essentially emergent hadronization showers of the twin QCD sector, which are displaced, which is a really, really striking signature at something like high luminosity, at something like the LHC. Can we go to figure 10? Oh, okay, sorry, I didn't even notice that. Brilliant. Figure 10. Okay, and so these are the sort of this is the sort of reach you would expect to get at high luminosity here, and this is with 300 inverse femtobarns. Along here, the x-axis is the mass of these twin glue balls. That's sort of model dependent. It depends on the details of the twin sector. And forget the left-hand axis. That's another type of model that we know is neutral naturalness. So another type of model where you have lots of new neutral ungauged particles, ungauged in the standard model gauge groups. But here we have the twin top partners. So they're these new heavy fermions which are gauge neutral. And you can see you can probe because of displaced vertices searches, very interesting range of parameter space as a function of the glue ball mass. But you can see that even with 300 inverse femtobarns, you wouldn't be constraining these twin top partners to be much more than like 600 GeV. It's pretty great that you can even get access to that. The experimental signatures are pretty spectacular. But going to high lumi, you can cover more parameter space. And if you see here, this is not scaling like root luminosity. You can actually calculate how these signatures would scale. And the branching ratio of the glue balls is scaling like something like 1 over twin top. The branching ratio of the Higgs into glue balls is scaling something like 1 over twin top mass to the 4th power. Yet, you can see you can go from twin top sector masses like at, say, 600 or 700 GeV all the way up to more than a TeV, even though the rate has gone down a lot. And the reason for that is that these are so spectacular that they're not limited by some large background. So it's almost all of the extra statistics, that factor of 10 statistics you get between 300 and 3,000 inverse femtobarns pays off, and you get to probe an awful lot more parameter space, even of this very peculiar possibility for nature. Okay, so I'm going to wrap up on the twin Higgs there. Are there any questions about it? Yes?
The way you explained the twin glue balls, etc., it seems like the twin sector is a whole twin standard model.
Yes.
And so isn't that the possibility, for example, that the light Higgs decays into two twin top, and then I have, or twin top, anti-twin top, and then I have some, I don't know, label mixing twin currents. I mean, why?
Right, so these twin tops are heavy. So F is bigger than V by quite a lot. And so these twin tops you should think of them in the back of your mind as being like 700 or 800 GeV, for instance. So the Higgs, the standard model Higgs can't decay into them. So it decays through a twin top loop to something, and the most accessible thing is twin glue balls. I'm going to anticipate what else you might be thinking about, because there's the question of, is this an exact twin copy or not? Because the most important features, so it could be an exact twin copy, then you have the twin photon, so cosmology gets a bit dangerous, but there are various possibilities on that front. However, for this whole question of naturalness and fine-tuning, it was really the twin top and twin gauge sectors that were the most important. So people talk about the identical twin, where it's an exact copy, or the fraternal twin, where it's not an exact copy. You could actually modify some of the details might be modified. It's a question. It's a very interesting question as to how much modification is too much, and what's the point of even introducing this if the exchange symmetry is only good in certain sectors and things like this. But that's a separate conversation. But it's not totally clear that it should be an exact copy or not as well. On top of that.
So maybe it's worth it maybe I need the clarification. If I remember well, I know that some twin models after the discovery of Higgs in 125 GeV was like wasn't available, like was a problem with this kind of models, and then this started to be modified to fit this kind of observation. I mean, I'm not sure what kind of model maybe of twin Higgs we're talking. Maybe that's one of the things that are confusing me a little bit. So I don't know if you can.
So 125 GeV Higgs isn't a problem for twin models.
Okay.
It's fairly okay.
As far as you remember well, maybe I'm wrong, but because of this exchange of symmetry, and this implies modification in the vacuum, rotation vacuum of this modeling, then if I see 125 GeV for one Higgs, then the other one should have a specific mass. But I'm not sure about this. It's in the back of my mind, and this is like bothering me, and I'm not sure.
Sure. So the twin is not an exact twin. You know, there was some breaking of the exchange symmetry, which made the twin Higgs a bit heavier. You know, like a lot heavier, 600 or 700 GeV. And you should really quantify these things in terms of mass squared, so that is a much bigger number. But it's not a problem. So problems with the Higgs mass and the LHC, when the LHC discovered it, the Higgs mass was a little bit too heavy for supersymmetry. There was tension there, and it's sort of a little bit too light for a standard composite scenario. It can be accommodated, but it's slightly uncomfortable. That might be what you're thinking, what you're remembering from 2012, or yes, Simon.
Maybe you can comment on the HL-LHC branching ratio. That might help with the question. The vanilla twin breaks up to a half.
Oh yeah, sure. Well, not just HBB-bar, HZZ, everything. Yeah. So if it's but we've already discussed it's not an exact. There's breaking that raises the mass of the other one, and so then the couplings go like V over F for the twin Higgs and to standard model fields, and V squared over F squared here. If it was an exact copy, then yes, as Simon's saying, then both Higgses would have equal branching ratios, and so that's ruled out. But that was known. I mean, that was known to be ruled out even before the LHCs turned on, because precision electro weak, everything would have been messed up already at LAP. But in terms of the mass, there's not a problem for the twin necessarily. There's a tension. It's a little bit too light for composite Higgs, a little bit too heavy for SUSY, but not in any sense that's sort of lethal to those models. No, this is a great question. Any other questions? Yep. So basically the fact that the quarks are heavier than the QCD scale. So there's nothing else really left. That's it. Yes, it's also interesting. So I'm highlighting this because it's something that's been studied. If the quarks are still, if the twin sector quarks happen to be lighter than the QCD sector, you would also have interesting hadronization. But that's sort of a model-dependent question. And then you get into hidden sector, twin sector hadronization, which is a whole interesting topic in its own right. And the hadron collider signatures are also very interesting. Okay, so maybe I should wrap up. So I've tried to give you a sort of sample of various things that could show up at high luminosity LHC that are interesting in BSM physics, and I've intentionally picked models, scenarios that give different signatures to try and map out, number one, where the opportunities lie at high luminosity LHC, but also the breadth of BSM signatures that one could talk about, right? There's an enormous breadth of possibilities for things that could still show up at high luminosity LHC. I think the lesson for me, at least, and you can take from it what you like, is that high Lumi is an amazing precision, will be an amazing precision machine. You know, we'll have 20 compared to now, we will have 20 times more Higgs bosons than we have at present, which is a lot. We'll have 20 times more W's and Z's, and there's a lot you can do with such a data set. It also means we can probe regions of phase space, you know, in distributions that are 20 times smaller than we can access now, in principle. However, to be able to benefit from all of that, we're going to need to beat down systematics. So in terms of theory systematics, QCD calculations, we will need more loops and more logs and more legs, more distributions. On the experimental side, probably more sidebands and neural nets, doing smart things like taking ratios of observables to cancel systematics and so on. And if we do that, it's perfectly plausible that some hidden in the data already, some 1 sigma deviation in some BSM search could potentially evolve to a discovery to something like 5 sigma in the future. And I think a big driver of progress on the BSM side is really going to be measuring things like Higgs couplings much more precisely than we currently have. But also, there are lots of interesting signatures involving exotica that are there waiting to be studied. To make progress, we're probably going to need to understand detectors even better than we do, which is not easy. Understand rare standard model processes that have yet to be calculated, for instance, and also develop new ideas for observables. But if we do all of that, then I think there's no guarantees. I'm certainly not going to guarantee for you that there's going to be some BSM discovery at the high luminosity LHC, but for sure the doors lie wide open for it if it's lying there around the corner. And I should wrap up. I think I've finished just on time, I guess.